Hi folks, it's Glenn, and I'm making a little video here for your Module 7. And it is because I couldn't find a suitable video that lumps everything that you need to know for this week's work together in one spot. So the first problem that you encounter on the WebAssign asks about chemical bonds. I have silicon tetrachloride and calcium fluoride, and you're going to have some other compounds. Here are the formulas conveniently given to you. Now let me show you how to figure this out. Silicon tetrachloride, because it uses the prefix tetra, you know that this is going to be a molecular compound, meaning not an ionic compound. You may also have known this from Module 1 as a covalent compound, or from a previous module. It may not have been Module 1 necessarily. But because it is SiCl4, silicon tetrachloride, you put the Si in the middle. You can surround it with the Cl's. This is what is usually intended when a formula like this is written. Now, because of, let me just say it again, because they use the word tetra, you know that this is not an ionic compound. Also, because silicon is not a metal, it is a metalloid, and chlorine is also not a metal, this is not going to be an ionic compound. An ionic compound is made either of ions or of a metal and some nonmetal. In both cases, they're ions, but there is a case where there can be no metals and still there could still be an ionic compound. But the other compound was calcium fluoride, like this, right? And because this is a metal and this is a nonmetal, you can know that this is an ionic compound. Okay, let me show you how to figure out how many bonds there are. Chemical bonds exist between two atoms at a time. So between these guys, you could have a chemical bond. Between these guys, a chemical bond. These. All the atoms in a compound are linked by a chemical bond. If there's an atom that is not linked by a chemical bond, then it is not part of this compound. It is just floating around nearby. Okay? So here I have 4 bonds, and because the prefix tetra was used, or if you prefer, because none of these are metals and none of these are polyatomic ions, I know that these are all covalent bonds. What you need to figure out is, are they polar covalent or are they nonpolar covalent? And to apply that concept, you're going to have to sophisticate your understanding of covalent and ionic bonds a little more. Before we do that, let me finish drawing this one over here. So calcium is a 2+ ion, and you know that by looking at the periodic table. Here it is. Calcium is in group 2 here. Okay. Fluorine forms the 1- ion fluoride. And you know that because fluorine is here. It is only 1 step away from the right. 1 step, that means 1 negative charge. So fluorine becomes fluoride with 1 negative charge. And we usually draw this out, if we're drawing, using brackets. And the reason is simply because fluorine owns all of those electrons. None of these electrons are shared. Let me just start that one over. So calcium, and then fluorine, and then fluorine, and bracket, fluoride, bracket. Okay, so the electrons that fluoride has are not shared. And the fluoride, I'm going to now draw the valence electrons for fluoride. Fluoride has 8 valence electrons. Here's how I know. Fluorine has 7 valence electrons because it is in group 17. These guys have 6 valence electrons. These guys have 5. These guys have 4. These guys have 3. Now, fluorine, having 7 valence electrons, gains an electron to become fluoride. So it gains 1 electron. 7 plus 1 is 8. So that's how I know that fluoride has 8 valence electrons. I'm going to draw them. 1, 2, 3, 4, 5, 6, 7, 8. Notice that I've drawn the electrons as though they were sitting on a box around the F. So 1, 2, 3, 4, 5, 6, 7, 8. I did that because it's important in chemistry to know which electrons can be paired with some other electron and which ones can't. The target number of electrons that almost every atom behaves as though it wants is 8. And a box conveniently has 4 sides, and 4 times 2 is 8. When electrons are paired like this, they no longer seek to react. When electrons are all paired, the atom that owns those electrons is no longer reactive. It is not going to easily do some chemical reaction to form some new compound. What about, so this is F minus. What about before the minus is acquired on fluorine, before fluorine becomes fluoride? It has 1, 2, 3, 4, 5, 6, 7 electrons. Notice that I know that fluorine has 7 electrons because it is in group 17. It is 1 step away from the end, where everybody at the end has 8 valence electrons. Okay? Remember from a previous module that fluorine actually has 9 electrons. So I'm only talking about the valence electrons here, because in chemistry, all of the chemical reactions happen because of the valence electrons, not because of any other electrons, not the inner electrons. Now, when you draw an atom and its valence electrons, it's important that you draw them on one side of the imaginary box at a time. When you draw them on one side of the imaginary box at a time, you can avoid errors. For example, aluminum has 3 valence electrons. This is an error. This here suggests that one electron is going to be reactive, going to participate in new chemical bonds, and a pair of electrons are not going to go reactive. They're just going to stay together. Electrons do prefer to stay in pairs. That's how they are stable in nature. When you draw one atom per side of the imaginary box, you follow nature's pattern in that aluminum's valence electrons, there are 3 of them, are all reactive. Aluminum will lose all of these electrons in some ionic bond formation process. For example, if aluminum reacts with chloride or with some chlorine atoms. The chlorine atoms have 7 valence electrons. Here, actually, let me go to fluorine because you're familiar with fluorine, and I don't have to show you the periodic table again. So 1, 2, 3, 4, 5, 6, 7. This is just 1 right here. Okay, so fluorine has 7 valence electrons. This electron from aluminum will leave, and it will stick to fluorine. Fluorine will become fluoride. It is negatively charged. Aluminum is now 1 plus. Another fluorine will come in here. 1, 2, 3, 4, 5, 6, 7. With its 7 valence electrons, this is unpaired, therefore reactive. This is also unpaired, therefore reactive. So this will come here and join this other reactive electron, and fluorine will own all of them and become F minus. This is fluoride. This will keep on happening until all of the valence electrons are paired, like that. All right? So then you get the compound AlF3. Similar thing happened with CaF2. Ca, having 2 valence electrons, is not like this. Ca having 2 valence electrons is like this. Now, I usually start from the top and I go clockwise on my imaginary box, but it's not necessary to do that. You can start anywhere you want. As long as you keep on going in one direction, it could be counterclockwise or clockwise, putting 1 dot on each side of the imaginary box at a time. This modeling that I'm doing helps you and me to understand why chemicals bond. Why chemical bonds form. This type of model is called a Lewis dot diagram. Obviously, it's called dot diagram because of the dots. The dots mean the dots signify the valence electrons only. Okay? More on the Lewis dot diagrams later. Okay, so you can tell that here I've got two chemical bonds. One bond between the calcium and the fluoride, and another bond between the calcium and the other fluoride. So let me draw these dots. You should draw the minus sign outside of here, just just so it doesn't get mixed. You don't mix them up with the dots. But it's not critical. It isn't as though you're going to draw structures and I'm going to grade them. So uh, there are two chemical bonds here. This is a chemical bond between the calcium and fluoride, and this is a chemical bond between the calcium and fluoride. Of course, these are called ionic bonds. And the nature of the ionic bond is just the attraction between plus and minus charges. That's all it is. It's very, very strong, though. If you were to try to break this bond by heating this up, by melting the calcium fluoride, you would have to go to huge temperatures. Temperatures that are not available on the planet Earth in nature. You would have to go, well, I guess you go to the center of the Earth and then you would find such high temperatures. But I'm talking about temperatures like 700 degrees Celsius, that kind of high temperature. Of course, you do not need to use heat to break this bond. You could just dissolve this in water, and water has special properties that you will learn about in this module also. But water has some special properties that allows it to separate these ions and to break these ionic bonds very easily with addition of little or even no energy. So that is so this is two ionic bonds. I've got two ionic bonds here. Now I'm going to ask you to sophisticate your concept of ionic and covalent bonds in order to understand polar versus non-polar covalent bonds. The truth of the matter, folks, is that it is not the case that every metal and non-metal making a compound is going to make ionic bonds. Sometimes a metal and a nonmetal will make covalent bonds. For this class, you can always assume that if you see a metal and a nonmetal, there are ionic bonds rather than covalent bonds. But when I show you the difference between polar and nonpolar covalent bonds, you're going to see some evidence that would suggest that metals and nonmetals can make at least partially covalent bonds, and then you'd be right. So here we go. Okay, this is just hold on to your hats. Try to be patient with this. It's a very fuzzy concept, right? It's not necessarily black and white. Here we go. So here I have a little tool that allows me to take two atoms here, and I can pick what the electronegativity of the atoms is going to be. This word, electronegativity, it means the attraction that the atom has for electrons in the bond. Okay, so here I have one atom that is very highly that has a very high attraction for the atoms in between the two. I'm sorry. Here I have an atom that has a very high attraction for the electrons in between these two atoms. Any electron that falls in between these two atoms, this guy has a very high a very high attraction for. Now this guy, compared to that guy, 0.7 compared to 4, this guy has a very low attraction for any electrons that falls in between these two atoms. This is a nucleus, this is a nucleus, and these clouds, this blue cloud is the electrons, this red cloud is the electrons. You could see that here, let me just make this a little easier to see. 1, okay, so this is about 1. I have an electronegativity of 1, an electronegativity of 4 over here. There are two different atoms, two different elements. You could see that this guy has an electronegativity that is 4 times higher than the electronegativity of this guy. That means the attraction for electrons by this atom, the attraction for electrons that are in between these two atoms. This guy has an attraction that's 4 times stronger than this guy. So what does that mean? That means that this guy is going to make an ionic bond. But notice that the definition of ionic bond compared to polar covalent, compared to nonpolar covalent, is very fuzzy here. There isn't a defined gap or a defined line that divides ionic, polar covalent, and nonpolar covalent. It's kind of fuzzy. I can change the electronegativities so that, look at this green double arrow right here. Is this bond right here, the bond between these two atoms, is it polar covalent or is it ionic? In fact, nature doesn't care if you call it polar covalent or ionic. We just call things polar covalent, ionic, and nonpolar covalent in order to understand. This is our model of understanding nature. As you could see, it is so imperfect. Nature is doing her own thing, and we're trying our best to describe it, but the best we could do is still not good enough. It doesn't fully describe nature. You could see that you could make a little argument. Oh, it's actually more polar covalent, but then the other person could say, no, it's really more ionic. And your textbook gives you a hard definition for you, okay? Let me show you the page. I have seen textbooks with different definitions. Your textbook says if the difference in electronegativity between the two atoms is greater than 1.8, then we're going to call it ionic. If the difference in electronegativity between the two atoms is less than 0.4, then we're going to call it pure covalent. Otherwise, also known as nonpolar covalent. When your book says pure covalent, they're talking about nonpolar covalent. Okay? So, I know what you're thinking. You're thinking, yeah, but what about if it's 0.4? What if it's exactly 0.4? 0.4 is not less than 0.4, and 0.4 is not between 0.4 and 1.8. So what about when it is 0.4? See, your textbook can't really help you with that. Your textbook is just not helpful. So the truth is, nature doesn't care. You can call that here. Let me show you the difference of 0.4. Oh, okay. This tool doesn't even let you. Oh, actually, it does. Here, let me. There it is. 0.0. See, wait. This is 0.04. No, I wanted to show you 0.4. This tool doesn't even let you go to 0.4. Okay, well, I guess I cannot show you a 0.4 electronegativity difference, but the point is, these chemical bonds they can be more nonpolar covalent, or they can be more polar covalent, but they're not going to be perfectly polar covalent, or rarely are they going to be perfectly ionic. And however, they can be perfectly nonpolar covalent, and here's how. If you have an electronegativity of 3.56 for one of these guys, and 3.56 for one of these, 3.56 for one of these guys, and electronegativity of 3.56 for the other guy. See, this is the same element. This could be maybe an oxygen atom bonded to an oxygen atom. If they're the same element, then the bond is going to be perfectly nonpolar covalent, meaning it's going to be purely covalent. That means that the electrons in between these two atoms are shared evenly. If this guy decides, if this atom just by chance attracts an electron that is right here, this atom is going to be attracting that electron with the same force of attraction. So here you have something that is pure nonpolar covalent. But that's the only time anything's going to be pure. Even if you try to get the maximum the maximum electronegativity on one atom and the minimum electronegativity on the other atom, it may seem purely ionic to you, but this animation here, this picture shows you that there is some sharing right there. There's some sharing right there. So you may point to this and say, hey, this is not purely ionic, because the definition of an ionic bond is a chemical bond that is purely formed from the electrostatic attraction, the attraction between plus and minus charges. But this one, it looks like there's some sharing of electrons here too, and you would be right. You would be absolutely right. Here, let me show you some more on electronegativity. Here is a chart of electronegativity that looks like your periodic table. It looks like this. See, periodic table here, and here's electronegativity chart. Electronegativity is usually quantified on a 4-point scale, just like your grades. 4.0 is an A. It's also the highest electronegativity score. There are no units for this. These are just like grade points. There are no units. And the lowest on the lowest electronegativity in nature is cesium, which is 0.7. Notice that I can get a metal with a pretty high electronegativity, such as gold, right? A metal, gold. And I can get a non-metal with some pretty low electronegativity, such as, let's say, carbon. If I made a compound out of gold and carbon, from what you've learned in previous modules, it's a metal and a non-metal. So it will be gold carbide, metal and non-metal. That would be an ionic bond, right? Ha 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 ha. You can see what I'm talking about here, right? Gold has an electronegativity of 2.4. So here we go with 2.4. And carbon has an electronegativity of 2.5. So here we go with 2.5. So if you make gold carbide, no, it is not an ionic bond at all. Look, it's almost nonpolar covalent. So this is how your concept of ionic and covalent bonds needs to get sophisticated a little bit. It is actually not the case that any metal and non-metal are going to make a real ionic bond. For the purposes of any problems in homework or tests, yeah, you're going to call it an ionic bond. But if you tried to dissolve gold carbide in water, you are going to fail. It is not going to dissolve in water. It is not even going to dissolve in boiling water. I mean, some may dissolve, but most of it won't dissolve. Here's another example. Lead. Where's lead? Where's lead? Where's PB? Here it is. Lead is a metal, 1.9. And chloride, 3.0. Lead, chloride, metal, non-metal. It should be an ionic bond, but lead chloride does not dissolve in water. Well, it does. A tiny bit dissolves in water, but you can hardly notice that. If you put lead ions, lead 2+ ions in water, and chloride, Cl- ions in water, they're going to form this white powdery stuff at the bottom of your container. So this is another example of an ionic compound that really doesn't have fully ionic bonds at all. It has something that's more similar to a covalent bond. Okay, so anyways, I hope your concept of ionic and covalent bonds has become more sophisticated. Now, to decide whether these bonds are polar covalent or nonpolar covalent, you're going to have to consult the electronegativity chart. I like this chart because it shows you by height who is more electronegative than whom, but your textbook has a great chart, and it's flat, but it's still great. See the grade point averages are shown here. Ha ha ha. I mean, the electronegativity scores are shown here. It even shows you with arrows the patterns. you can see the patterns easily on this height chart. As you go to the right on the periodic table, you could see that generally the electronegativity increases. As you go down a column, down a group on the periodic table, as you go down here, generally the electronegativity decreases. Okay? Decreases. Now, why are these noble gases not participating? Why do they have no electronegativity score? It's because, remember, the definition of electronegativity is the attraction that an atom has for electrons in a chemical bond. The trouble with noble gases is that they do not make chemical bonds, except under extraordinary conditions, which you usually have to apply yourself in a lab. I mean, nature will hardly ever provide the extraordinary conditions necessary for causing these noble gas elements to form chemical bonds with anything, even themselves. And so that's why these guys are not involved. So that is how to figure out the number one here. Now let's have a look at number two. Bond enthalpy and bond length. Yeah, I have a little graph for you about bond enthalpy and bond length. You can consider bond enthalpy as the same as bond energy. Enthalpy is a form of energy that includes it is all the energy that is inside a chemical bond. Okay, so when you make a chemical bond, usually energy is released. A lot of that energy is released as heat, and you no longer have access to that energy. I mean, it goes away in random ways into the surroundings. So oftentimes that heat energy is not considered useful. However, when the word enthalpy is used, all the energy is considered here. So including the heat energy that would be lost when you form a bond, or the heat energy that you have to input in order to break this bond. Okay, so anyways, bond enthalpy is just bond energy. So when the bond enthalpy is low, you could see that this is low, this is higher, this is higher. When the bond enthalpy is low, what is the bond length like? These numbers are going from low to high. These numbers are going from high to low. Now, does it make sense to you in a common sense kind of way that a high bond energy is going to correspond to a, does it make sense to you that a low bond energy, 300 compared to 600 or 800, a low bond energy is going to correspond to a higher bond length? Let me draw this. Let's see. So here I have an atom, and it's bonded to another atom. Here's an atom, and it's bonded to another atom. So the energy that is trapped in this bond, and the energy that is trapped in this bond, you may think that because the bond is larger, the energy should be larger. But see, the energy is doing a job here. This energy comes from forces of attraction. It's an attractive kind of energy. So the forces of attraction are obviously stronger here. I mean, if these were human couples, right, and they were at a party, if these couples were inseparable, I mean, if they were all over each other all the time, then, you know, the bond is stronger. So the bond energy is higher. Whereas this couple, you know, oh, hey, how's it going? All right, yeah, I'm going to go over here and get some sandwiches. All right, so these guys, they have a weaker bond. So the bond energy is lower. So this is how you can understand this. Now, I'll let you figure out the answer to that. Now, this is known as, this curve is known as the Leonard-Jones potential, and it's pretty famous. I think there is some mention of the equation for this graph. So this graph is a theoretical graph. I mean, scientists came up with some math which would describe how atoms bond and why atoms bond. And they came up with that math like this. It is an equation. Here it is. This is the math they came up with. And if you were to graph this with the bond energy, or the energy that exists in between the two atoms as the y-axis, and then the distance between the two atoms on the x-axis, you end up with a graph that looks like that. And I've done that for you on this special graphing website. I've copied that equation. This is the equation. There's a 12th power, there's a 6th power. There's a 12th power, there's a 6th power. Oh, did I get that backwards? Oh, I did get that backwards. Whoops. Okay. So here, let me fix that for you. 12th power and a 6th power, and make this a positive, and okay. Oops. So make this positive. Okay. Oops. Okay. So sorry, that was backwards. All right. So this is the graph. So I have graphed the equation for you. I'm only, this equation actually goes both ways, positive and negative, but the meaning of the x is the distance in between two atoms, and so you can't have a negative distance in between two atoms. So I'll just make this graph only for positive x. So let me explain to you the meaning of this graph using someone else's YouTube video. But before I do that, let me make this a little clearer. This is the math that scientists came up with, right? And when they graphed it, the graph looks like this. Or you can change the scale of the x-axis. You can, stretch out the x-axis to make it look prettier, like this. And then they found that this is the energy of the bond. So the bond enthalpy that you saw in the previous problem, that's what this is right here. In the previous problem, the bond enthalpy was given in units of kilojoules. In this graph, the bond enthalpy is given in units of electron volts. Now, the bond enthalpy, when scientists did an experiment to see if this equation is correct, they found that yes, if you try to separate, if you bring two atoms close together and you try to separate them farther apart, the bond enthalpy really is some number that's very close to this. So this graph coming from that equation that scientists came up with matches what happens in nature. So this is how chemistry often happens. People have an idea that involves math, which they believe should match the way nature works. And then they graph that or something, and then they do experiments to see if the experiment yields the same numbers that are indicated on that graph. Like this is the distance in between the two atoms when the chemical bond is made. And this is the energy that you get when the chemical bond is made, or the energy that you need in order to break the chemical bond. This is that bond energy. And so when the numbers match between the theory, the math, and the experiment, then a discovery is made. So that's not always how it works, but that's often how it works. Now, let me go to this YouTube video to help you to understand the meaning of the graph and the equation. I'm not going to play it because it's too long, but it's only 3 minutes, but it just goes, it does some unnecessary detail for us. So I'll just play part of it. So the x-axis means distance between two atoms. So let's say that you have a hydrogen atom, and we keep it here, and another hydrogen atom, and we keep it here. Because the x-axis means the distance in between the two atoms, this hydrogen atom is going to move closer and closer and closer this way to decrease the distance between the two atoms. Here, let me show you. You see that? Yeah, it's moving closer, okay? Now, as it moves closer, the energy, some energy gets released. When you move two hydrogen atoms close to each other in nature, you're going to get some heat. The energy is released as heat. Sometimes the energy is released as light. But on this graph, any release of energy is shown by a drop in the potential energy of these two atoms. Okay, potential energy is the potential energy on this graph is very similar to the potential energy that you have if you're on a hill. If you are standing on a hill, you may not feel particularly energetic, but you have potential energy, because if you were to start rolling, you would roll down the hill, and I wouldn't have to push you anymore. I just have to get you started rolling, and you would just keep on rolling. So that potential energy is getting converted into energy of motion. That's what's happening here. These two atoms, because they are far from each other, we say that they have potential energy. Okay, they have a certain amount of potential energy. Let's call it 0. But when they start coming closer to each other, energy is all of a sudden released, and we start feeling heat, or we start seeing light. It's because they're releasing energy. Where did they get this energy? That energy just comes from the fact that they were far apart from each other. When they come close to each other, some attraction is satisfied. And that attraction, the satisfaction of that attraction, is released as heat or light. What is that attraction? It's the attraction between the nucleus of one of these atoms and the electron of another atom. It's between the nucleus of one of these atoms and the electron of the other atom. Okay? So when those things start to attract and they start coming close to each other, they're going to start speeding up, because the closer they get, the stronger the attraction is. That speeding up right there, that is a release of energy. And we see that as heat or light. Okay? On the graph, we're just going to see it as moving down the hill. All right? So here we go. So it goes down the hill, just like that. Okay? So that is the meaning. Whoops. That is the meaning of this graph in your problem. So when two atoms are 1 unit apart, they may have a potential energy of 0, but as they come closer together, like let's say half a unit apart, then their potential energy is going to be negative, meaning some energy has been released, meaning they're going to start, they are now moving closer to each other faster and faster. The atoms, see this as, oh, we're moving closer to each other faster and faster. But we see that as, oh, those atoms are giving off heat or light. So that's what's going on with this graph. Now, at the bottom here, the atoms have released all, at the bottom of this graph, the atoms have released all the energy that they can. So at this bottom quantity right here on the y-axis, what is this? Negative 4.26. So from 0 down to negative 4.26. That signifies a 4.26 electron volt release of energy. So that's the bond enthalpy. That's how much energy that's how much energy is in this bond. Okay. I hope that makes sense. Now, what about when the atoms get closer, even closer to each other? So this right here, this 0.236 nanometers, this is the bond distance. This is how long the bond is, the bond length. The same as from the previous problem. This is the bond length. Okay? So, let's see. What if you squeeze those two atoms even closer? So they're 0.2 units apart, 0.1 unit apart, or even closer. Let's see what happens in the YouTube video. So, coming closer to each other, coming closer to each other. Okay. Right around here. I think they show you, yeah, they show you right here. See, these atoms are coming closer to each other right there. And when they come closer to each other, they're too close. They're so close that the nuclei can feel each other's positive charge, and they start to repel. And the electrons can also feel each other's negative charge, and they start to repel, because negative charges repel other negative charges. Positive charges repel other positive charges. So as they start to repel, the the, the these atoms feel a force of repulsion pushing them apart. So I am trying to push them together to see what happens. They are trying to push apart. So I have to use more and more energy to push them together. That is what is indicated by the positive portion of this curve. Let me do it on your graph. You see this positive portion right here? This is and all this is energy that I have to put in order to push these guys together. Okay. So that's the story of this graph. It's kind of interesting that these days there is a lot of talk of climate change because of too much carbon dioxide in the atmosphere, and too much carbon dioxide in the atmosphere causes global temperatures to rise on average because of this graph. I mean, here, let me show you on the same video. When you have chemicals that are bonded, it's right about here. When you have chemicals that are bonded, and then those chemicals start to, yeah, this is fast. Sorry. When those chemicals, when a molecule starts to stretch its bond, that only happens if there is some heat available. So you see this bouncing up and down. This is every time it goes up, it is absorbing energy, and every time it goes down, it is releasing energy. Right? Up, absorbing, down, releasing. Up, absorbing, down, releasing. So the reason why the carbon dioxide molecule is able to absorb heat so much is because every time heat from the sun gets reflected off the earth and hits a carbon dioxide molecule, that carbon dioxide molecule goes up in potential energy. It absorbs that heat, right? And when it absorbs that heat, its bond gets, its chemical bonds it shrinks, right? But then it's going to have to release that because that's what things do. Things go downhill in terms of energy. That's what you would do if I nudged you down a hill. And that's what carbon dioxide does in terms of energy. If it absorbs some heat, it's going to go down. And when it goes down, it's going to release that heat. It's going to release that heat back to Earth so that the heat stays here instead of exiting the planet and going out into space. So you could see that they do it with this hydrogen molecule, but in the news, or in some news, we are having that done in our atmosphere, mostly by methane, carbon dioxide, water molecules, other molecules. They just keep on doing that. They just get hit by some heat, not a lot of heat. It just could be room temperature level heat, and then they just absorb that heat and shine it right back, right back down to the planet. So that's kind of interesting. Now, what are they asking here, actually? The bond strength between the sodium and the chlorine atoms. Okay, so the bond strength is 4.26 electron volts. That's the bond strength. 4.26 electron volts. I hope I'm right about that, because if I'm not right, I might have to start all over again. Right, so I'm going to oh yeah, maybe I can see if I'm right now. I'm going to continue the rest on another, oh, I am right. Okay, that's good. So I'm going to have to continue the rest of this on another video because this video is already too long. All right, so that's it. Thank you.